Today we're going to talk about networking with TCP, and we'll have a discussion on HTTP. Why don't we talk a bit about yesterday's stuff? Yesterday we talked about asynchronous operations along with callbacks. So how's everyone feeling about yesterday's stuff? Is it like super simple, or what the hell is that? Let's take a straw poll. Let's get you to check your SS or WTH, or your favorite WT if you want. So let's get some people to, we have 23 people online. Let's get 23 responses in the chat. So super simple or what the hell, as far as, so half super simple and half what the hell. Okay, 50-50. Someone says, I can't even tell what the answer to that. Okay. What the hell, what the hell? A lot of what the hells. Okay, at least we got there all what the hells as opposed to anything else. So great. Okay. All right. So we'll do a quick review on asynchronous. And the important thing to remember about JavaScript is can not be interrupted. If I can spell it right. JavaScript cannot be interrupted. It is what's called a single-threaded process. It is a non-preemptive, if you want to use the technical term, a non-preemptive process. It can't be preempted, which means if I have 2 or 3 lines of code, those you can be guaranteed that those 2 or 3 lines of code will execute one after the other, and nothing will happen in between 2 lines of code. Multi-threaded processes or languages, you don't have that guarantee. If you're using multiple threads, you might have something happen between. Let's say I've got a, I don't know, const. We'll go let. We'll go let num equal 5 console log num. So if I have this in JavaScript, it's pretty darn clear that, well, I have line 19, and when I console log num, I'm going to console log 5. But with a preemptive multitasking language, that might not be the case. There may be another thread that also has access to that num. It may decide that it's going to go in another thread, num plus plus, for whatever reason. And you have no guarantee when that's going to happen. It might happen right in between there. Like, wow, now there's a what the hell. Like, what the heck? So there's ways we manage this stuff in these languages. We make sure things happen together. We say we insist these things run together. You can do different things. But JavaScript does not have that problem. Great question. What are the advantages of multitasking languages in comparison? Awesome question. Let's talk about that. So it all boils down to one problem, doesn't it? We want to do long running stuff, right? Things like file fetches. So file read, maybe a, HTTP query or something that takes time. And for things that take time, well, the computer is busy, or the JavaScript is busy doing something. And if we didn't have the ability to do more than one thing at once, it would block. It's called blocking. So if I'm reading a file and I have really a single-threaded, non-asynchronous, non-multi-threaded, non-preemptive system, that file is just going to, read, and nothing else is going to happen until that finishes. Anybody remember in an operating system called MS-DOS? Anybody remember that? Anybody heard of MS-DOS? That's like in the archives of computer history. That was actually the precursor to Windows. It was the original operating system of the PC, Actually, it's called PC-DOS when it first came out, but it was MS-DOS because Microsoft made their own because, well, IBM kind of screwed it up, but anyway. So MS-DOS. I still remember MS-DOS 3.1. It was great. That was single-threaded, non-preemptive, non-multitasking. When you did something, that's what happened. You had the entire power of the computer focused on your one task, and that was it. So we had to do all kinds of really interesting tricks to make things happen or appear to happen in threads. So the problem, of course, is blocking. Because when the computer or your process is busy, it can't do anything else. It's concentrating on that task. So there's various ways to do that. The two main ways are this: threads, or more specifically, multi-threading, at least from a programming point of view. Multi-threading or async. Multi-threading, this is what languages like C, C++, Java, this is what they can do. As a developer, you can see, oh, I want to start another thread. Start thread, run this stuff. There, keep going, do my stuff. Oh, another thread. You can start tons of threads. I've seen systems that start a for loop, and each for loop starts a thread going. It's pretty cool stuff. Very, very powerful. You can do all kinds of really cool stuff, but it does, take a lot of overhead and planning and software development to manage those threads. Because what do we do when a thread's done? Well, we have to notify, that, oh, this thread is done, and handle that notification that this thread is done, which of course sounds a lot like asynchronous programming. The difference is in multi-threading in software development is the multi-threading is built into the language. You can say open new thread or fork. Actually, the command is actually fork. Fork a new thread, and it will fork off. And you get two copies of your CPU, and one goes off one direction, one goes the other. Okay. With asynchronous, the language itself is single-threaded. So the language is single-threaded. Like JavaScript. JavaScript is single-threaded. It doesn't fork. It simply runs one thing at a time. But your operating system, so Mac OS, Linux, Windows, those operating systems, those are most certainly multi-threaded. So even though JavaScript is single-threaded, your computer, that's got tons of threads. It can do hundreds of things, thousands of things at once. So it is perfectly capable of handling more than one thing at the same time. And that's the key of how asynchronous programming works, is that it can do more than one thing at once in the operating system while keeping the JavaScript code mostly clean, so you don't have to think about that stuff happening. Now, you need to have a way, if you send something off the operating system, you say, okay, I want to read a file. Okay, well, I don't want to do this myself because this looks like it's going to take some time. I'm going to send that little task to my Mac OS, to my Windows, or my Linux. So, hey, here, Linux, take care of that file read. And then I carry on. But I'm going to need to know when that's finished. Because I can't wait for it to be finished because I want to carry on, because if I wait, that's the same as blocking, which means I will simply be sitting there doing nothing else while I'm waiting for that file to be read. So I need to have some way to be notified by the operating system that this got done. And that's where callbacks come in. It's the example of a telephone or a telephone number. Has anybody used a telephone? I'm sure everyone has. Has anybody given someone their telephone number? Anybody? I'll assume there's a couple of yeses there. Yes, or email address, or text message number. More it's SMS now, so. Okay, So if you've given someone your number, you've essentially given them a callback. Here's my number, call me back. For example, I'm doing some stuff. It's like, oh, I'm getting kind of hungry here. I've been coding for like, 9 hours and haven't eaten breakfast yet. Like, why is my head hurting? Holy crap, I haven't eaten. It's like 4 p.m. I better get some food. So I want some pizza. So I'm going to call the pizza place and say, hey, I want a pizza. When you're done my pizza, let me know when it's done. Here's my text number. Please call me back when my pizza's ready. Now, what do? Do I simply sit there and look at my phone, hoping and praying that number? Well, of course, if I'm hungry enough, I will. It's like, I'm hungry, please text me, I'm hungry. Probably I'm going to carry on with my code because I've got a deadline or something. I'm doing a lot of work. So I'm going to keep working. I'm not going to wait or block myself for that pizza to be delivered, although I am pretty darn hungry. Eventually, when I have time, because maybe they texted me, but I got really involved in some code, like, oh, I've got this thing I want to get done. This is really cool. Oh, look at this. I got this WebSocket thing working. Oh, it's awesome. Okay, take a break. I'm done for now. Okay, now I have some time on my hands. Take a bathroom break, that kind of thing. Oh, let me check my messages. Whoa, my pizza's ready. Awesome. So I didn't wait around and I didn't check my messages until I wasn't busy. When I was busy, I didn't have time to check my messages. I was doing something else. When I'm finished what I was doing, then I have time to check my messages. JavaScript is exactly the same. It cannot be interrupted. But when it's not busy, it will check for messages. We've all heard of the event loop, and where JavaScript gets notified of events or things that have happened. When JavaScript is not busy, it will check that. It will check, is there anything outstanding? And is there anything, do I have any messages, any events that have come up in my queue, the things that have happened? And that's how JavaScript handles it. So when I'm not busy, check messages. Ah, pizza, great, awesome. They've sent me a message back. That's my callback. But callbacks don't get fired or don't get executed until JavaScript is not busy. When is JavaScript not busy? When the current code is done, the current thread, if you will, because JavaScript is single threaded. So you have your main thread, start the program, go to the end. When something happens, a callback is called. That's now another main thread. When that callback is finished, JavaScript's not busy again. It can look around for more messages. What have I got? Okay, so that's really the core of how JavaScript handles asynchronous. And because it's not multi-threaded, it has to send work off to the operating system. Let's do a quick example, one we've all seen before. If I got one here, let's make a new file. Async. Okay, and what we'll do the example of the other file read using fs. So const fs. We've all seen this one probably. Oops. Const fs equals, and we'll require fs. We all know about require now. We have to pull in things that aren't built into the language. Although fs is built in the fs module, you get built into JavaScript, so you don't have to actually npm install it, thank goodness. But you still have to require it because it's something it's not one of the, or it's not built into the actual core of JavaScript. Okay, and make myself a callback. Call up my callback. There. Got a callback function. And I know that generally with JavaScript, I know that the fs.read file function expects the callback to look a certain way. Why? Because it just does. I'm sorry, that's their rules. You want to use read file, they're telling you got to give it a callback that looks like this. It has two parameters, error and data. And when they call my callback, they're going to give me my information back in these two parameters. If there's an error, they're going to fill that in. If there's data, they'll fill that in, and that'll probably be null. So that's what the callback looks like. Okay. And I'm just going to console log. I'll just log really callback runs. Why not? My callback. Because I don't really care that much about what's going to happen here. Was called there. That's it. That's a callback. I'm declaring a function. I'm taking this function, that stuff, and I'm putting that in a variable. Important to note, when you see a line like this, and someone asks you, what does that line do? What does that line do? Line 3. Well, line 3 does one thing only. It creates a variable called myCallback and puts that stuff inside it, a function declaration. It doesn't execute the function, barely looks at it. It just takes that stuff and sticks it inside that variable, and that's it. Okay. There's line 3. So now we have a callback. So we'll do an fs.read file. Read file. And fs.read file takes several parameters, and they're optional, some of them. We'll give them 3 of them. It takes a file to read. So we're going to try and read our own file, async.js, because we know we exist. We can give it a encoding, UTF-8, which we don't really care about right now, just for character encoding. What does it do? Who cares? You know, not important. Make it UTF-8 for now. And then it expects a third parameter. It says, okay, read file, where would you like me to call you back at? So ordering pizza. You betcha, sir. That'll be about 20 minutes. Where would you like us to call you? Or what's your number so we can call or text you when we're finished with the pizza? Oh yeah, here's my number, 778 something. Great, thank you. I give them my number. So I'm going to give them my callback. Now, has anybody wondered why it's this way and not executing the function like that? Because that's 2 separate things. What happens if we do this with 2 brackets in my callback? What happens there? Anyone?
It's gonna be returned like there is no return, but if we have return, then it's gonna return the value, like the result of the function.
Exactly. It's going to return undefined. It's going to execute the function. It's going to call the function, my callback. Well, my pizza example again. Okay. Yes, sir. Give us 20 minutes. Should be ready. Give us your number. Okay. I have my phone. Am I going to dial my phone? Okay. Here's what you're hearing. Oh, my voicemail. No, I'm not going to call my phone. I'm going to give them my phone number. So by executing my callback, I'm actually calling my phone, which is kind of pointless because all I'm going to hear is my voicemail. So, here's my voicemail, guys. Does that sound good? No, they want my number. They just want the name of the function. What is the function's name, or the function's phone number, if you will? Don't call the function, just give them the function. That's what they want. And that's the difference. And there oftentimes we kind of wonder when to use an execution like this and when to do this. We give it the name of the function if this read file will call that itself. And it will. When a read file is done, it will call my callback itself. Let's give that a try. So, see if I have this here. Got my vagrant. Is it here? There it is, async. Okay, let's call my my callback. So node async. Well, I got my callback was called, but that could have happened anywhere. You could have just print it out. So it doesn't really demonstrate what's happening. Let's add some more kind of interesting things here. Why don't we do this? I'm going to log just beginning of the fair. There we go, like this. There. And log something else. Let's say start of code. We'll just say start of code here. Start of main code. There. Okay. And at the end, let's do end of main code like this. Great. So now we can tell exactly when the main code starts and the main code ends. In fact, let's do something else. Let's maybe do something here. We'll log JavaScript is busy. So we ordered a pizza, or we ordered our read file, and we gave them our callback number. So they're going to start making that pizza for us, or they're going to start reading that file right there. Just to make it clear, when you call something like fs.readfile, it starts right away. It doesn't wait until JavaScript is finished. It's placing an order for pizza or an order for read file. So the pizza place is not going to wait until I'm not busy to start my pizza. They're going to start it right away. I sure hope not, because I want my pizza. So they will start my pizza immediately. The fs.read file starts right there. It starts chewing on that right away. My next line is JavaScript is busy doing stuff. Okay. JavaScript is still busy here. There. So let's watch what happens here. Run this. And there. Oh, my callback was called. Start of main code, end of main code, JavaScript was busy. And finally, JavaScript was not busy. Then my callback was called. There. I'll even say that. Okay, I'm not busy. Although technically, I guess it should be down there at the very end. So let's do that. Okay. Okay, so, okay, I'm not busy anymore. What have I got? Oh, a callback was in the queue. Let's call that. So this is how JavaScript works. Important to note that fs.readfile, once again, executes immediately. It starts chewing on that read file right away. Because once again, although JavaScript is single-threaded, your computer is not. It can handle that read file, no sweat, in a heartbeat. But JavaScript will never know until it reaches the end. Maybe that read file even finished in between those two lines. Pretty small file, chances are it did. But JavaScript has no way of knowing that. It's not going to know until it has time on its hands to check, did something happen? Oh yeah, my pizza's ready. Okay, let's do one more thing to demonstrate this. I'm going to actually say JavaScript's really busy. There. Let's do a for loop. And in this case, I will use a C-style for loop, which, as we all know, is exceedingly rare. I is less than, I don't know, 10,000? Sure, I plus plus. As we know, a C-style for loop is unbelievably rare in JavaScript, and certainly not something we would ever use to iterate an array, would we? Oh gosh, no, we'd never do that. Because that's not how you do it, JavaScript, unless you really need that I. So unless you need that I, and in my case, I need the I here, you would hardly ever see a C-style for loop like that. It's like unbelievably rare. Okay. All right. And for those of you who've done some work this week, we know that as well. So let's just do something. I'm going to make let's make a num equals, I plus, just doing some random calculations, I plus 1,000 or 100 there. And maybe if I is less than 5, there. I'm doing random code. I'll just console log num, there. Totally random stuff. Do this 1,000 times. Just some calculations, just to consume CPU time. And now this, this is taking a finite amount of time. Now this is, it's actually going to be busy. See what happens. That was pretty fast. In fact, anyone notice a delay there? Let's make it 100,000. Hold on. I want to see a bit of a delay there. Okay. Now it's 100,000. So hold on. There. I didn't see a delay. Anyone? JavaScript's really fast, isn't it? Like it's really, really fast. It's hard to comprehend the speed at which the computer can do calculations or do much of anything. So, and that becomes important later on. We talk in React Week. I'll talk about that. So one more thing. Let's make this. I want to see a bit of a pause to make it absolutely clear that this callback is not going to get called until the code. Okay. So let's do, I don't know, there. What's that? That's one. What's that number? Anyone? Looks like, is that 10 million? $10 million. Yeah, okay. I'm really bad at this. Okay, 10 million. Now that's got to be a bit of a delay now. Go on. Hold on, I'll do it again. Holy crap. Okay. 100 million loops. That's a lot of loops. Come on. I saw a bit of a delay. It did have to think about that 100 million times to do that for loop. Okay, I'll do one more. There, what is this? This is now 1 billion loops. Okay, I'm gonna loop 1 billion times. So now JavaScript really is busy. It couldn't possibly have time to check for callbacks. Let's try it now. Okay, 1 billion loops. Then it wasn't busy. Now it's probably pretty obvious or pretty likely that this read file finished long before the billionth iteration did it, but it still couldn't check because of the main thread. So that's how we work callbacks. A callback is simply what to do when it's finished. So this is an asynchronous function. Now my callback, that is not asynchronous. That's just a function. It's just a regular vanilla function. It's a callback function, but my callback itself, that's just console log. There's nothing asynchronous happening in my callback at all. This is all just regular synchronous code. Read file, that is an asynchronous function. So what does fs read file do when you call it? It immediately starts the read file and returns almost instantly. So lines 10 to 11 or 10 to 12, there is literally no delay. fs read file returns instantly. It starts the read file going, but it returns back, and we're on line 12 in a less than nanosecond. It looks, because I can do a billion things in that time. So it's pretty fast. So there is no time delay between lines 10 and 12. It starts the read file going, but then hits line 12 immediately. Okay, so that's a bit of a recap on asynchronous. Things to remember are JavaScript just can't be interrupted. It will check its messages when it's not busy. That's really the important thing to remember about JavaScript. One last thing, you might see fs or any kind of async function called with a callback this way. You also might see it called a more common way where they put the function in line. So, I mean, this is easy to understand. There's my phone number. You might see this. Just take this there. We can take that and put that there instead. There. Now, clearly, that's the same thing because my callback is in fact equal to that thing. So they are equal. So when something's equal, that means it is the same thing. So this is my callback. Well, same function anyway. So you would oftentimes see it written this way with the function inline. Sometimes that freaks people out, always freaks me out because it makes me more complicated. So they both work fine. You can have a separate callback with a name and call it this way, or you can do it inline like that. They are completely equivalent. Later on in React, you will find that we do this a lot. We make named callbacks to make our life easier rather than having them inline. But really, it works fine too. It can also be an arrow function. It can be like this instead, right? An arrow function. Same thing. Like this is way more common. You see this way without the function keyword. It's still the same thing. Okay. All right, let's move on to networking. What is networking? Has anybody done any networking before? And I don't mean, going to the bar, meet some guys, get some phone numbers. Oh man, get some investors and job contacts. This is, of course, computer networking or software networking. And we think of networking, oftentimes we think of, well, I got my home router. I can plug in my cable into my modem here, hook into a switch there, plug in my laptops into my Wi-Fi router. I got my Wi-Fi. So that's my network. And most of us have some semblance of a home network, even if it's as simple as a box that plugs into the Shaw, TELUS, or whatever, and Wi-Fi. That's still a network. Okay, so that's what most people think of as networking. But software developers, although that is perfectly correct, we think of networking in a slightly different way, or a more expanded way. We look at what's actually going on right from when you plug the cable in to when you see stuff on the screen. And there's a lot of stuff that goes on in between. And the concept is called the layers, or the ISO layers of networking, which we'll cover today. And it is perfectly okay to glaze over and not remember any of this. Just remember that there are layers, okay? We'll talk about those in a second. We'll do a quick TCP introduction, which is the most common type of a protocol for networking. We'll do a quick TCP net demo. We'll be doing that in Compass today too. We'll talk about some of the popular protocols. What are protocols? Yes. Of which HTTP is one. We'll talk about HTTP. Well, now we're getting to stuff that sounds interesting. HTTP, / google.com. We'll do a HTTP client example, and we'll use something called an HTTP browser. There's these really cool applications out there. They're called browsers, and they do HTTP calls. And we'll show you an example of our actual browser in the wild. Okay, we'll go through that. And what it does, more specifically, how this browser does its thing and what it does behind the scenes. So let's talk about, I love this, the layers networking. Funny story, when I started my first job, which years ago, I think it did not predate networking, okay? And as I've told people, contrary to popular belief, I did not first program on punch cards. But I do remember seeing a punch card machine in the corner of a lab someplace in my first year engineering. It's like, what's that machine? It's like, yeah. So although I did program on paper, they had these things called deck writers, and your code would come out in paper. You hit enter, it's crazy. So anyway, all right. So the OSI layers networking. Kind of two sets of layers. There are 7 of them. Anyway, back to my story. I got my first job. I ended up I was working in Calgary at the time for a company. First job out of university, like, wow. And they sent me on some courses because it was a big company. They just send the people away, and it was great. Business class flight over to Ottawa. It was really cool, right? So a couple of us went there, and I took this networking course. And I remember sitting in the classroom, and my only goal in this course was to wait until I can get out of the classroom, go back to the hotel, have some dinner, wait till midnight, and get over to Hull, right? Go across the bridge and party in Hull, because the bar is open at midnight over there, right? Or 1 o'clock something. Okay, that was my goal. So I remember sitting there, and this guy's talking about the layers of networking. I just kind of like, oh, what is this? What is this stuff? Wow, it sounds really complicated. Do I ever need to know this stuff? And all that I remembered from that lecture was there was a thing called the layers in networking. That's all I remembered. And I turned out kind of okay. So let's go through them really quickly. I'm not going to spend a lot of time on them. There's the physical layer, layer 1. That is the cables, Ethernet cables, USB cables, fiber optic cables. That's what you actually see. When you're doing stuff in your home network, you work on layer 1. You're plugging a cable in. So a network cable can carry a signal. So can a fiber optic, so can a USB. So they can all carry network media. Okay, it's a physical layer. We have what's called the data link layer, layer 2. This is where MAC addresses come in. You may know that you have a MAC address on your phone, your computer. Those are kind of hardwired into that device. So my phone's old too. time for a new phone, has a MAC address that was assigned to it by the manufacturer. It is unique to this device. No other device, I sure hope not, has this MAC address, although it's not a huge deal on a private network, but very likely no other device in the known universe has this MAC address. So it's unique to this hardware. It's baked into there. And that's how at the lowest level of firmware software that devices can communicate over MAC addresses. That's way down below what we care about, way down below TCP IP and IP addresses. Okay. There's also Wi-Fi protocol, which is slightly different, and PPP. Does anybody remember the term dial-up internet? Anybody? Go on, let's see at least one yes. Has anybody heard that modem sound? Remember that sound? You still hear it in movies now, as if it's like a thing. That weird modem syncing sound. Yeah, we used to use that. I had a modem. It's like it took forever to connect. Like especially when they got really fast, these 56K modems, which sounded fast back then. But dial-up wrote a lot of online games. Yeah, exactly. Yeah, so dial-up internet. Wow. So that's PPP, point-to-point protocol. It uses that to make its synchronization stuff. So it communicates that way. Really cool. So this is kind of the lowest of these software layers, just above physical, really low level. It's hardware. It's called L2. Anyone heard this term L2 switch, a layer 2 switch? That's a switch. Do I have one here? What do I got here? Like this, like this. I got lots of stuff. Anyway, I got a switcher somewhere. Probably if you have a switch, we call them hubs, but actually a hub is different. A switch is what's called an L2 switch. You plug your cables into them, 1, 2, 3, 4, 5. Maybe your cable modem has 4 or 5 places to plug in. So it has an integrated switch. Chances are it's an L2 switch. There is actually an L1 switch, which is called a hub. They don't sell those anymore. They are literally on layer 1. They replicate, they're horribly inefficient. So L2, anyway, going too slow. Okay, so layer 2. Just to know that there is a layer 1, there's layer 2, and one of them is physical. So one of those layers is the cords and maybe increasing complexity as you go higher. So the network layer. Now we're talking stuff that gets kind of interesting. IP addresses. That's kind of cool. NAT, network address translation, and ARP. Now we probably heard of things called IP addresses. Has anybody heard of the term? I'm sure we have somewhere heard the term IP address. What's your IP address? Like, as if that's a thing. Like, hey, hi, I'm Gary. What's your IP address? Yeah, mine's like that too. Oh, awesome, man. We have a thing. Yeah, it doesn't work. Trust me. So IP address, and they have a format such as 10 dot or 20 dot, 2.3.4. They're basically, at least for version 4, they're a group of 4 numbers. They're actually hexadecimal, but we talk like this. So maybe 164.2.4.5. Let's take a look. Let's find out what my IP address is. Let's go to Google, and we'll see what is my actual IP address on the internet. I love saying internet. Anybody watch the IT crowd? Come on, there's got at least one IT crowd fan in the group. I think that's a requirement to get a job in some places, is to have watched the IT crowd. So the internet, yes, okay. So what's my IP? My IP address is 38.34.73.156. That is my secret. That's my secret IP address. Everyone knows it now. Quick, close that. So that is my IP address, my public IP address. Inside your house, you probably have what are called private IP addresses that your router itself gives all your devices. But to the outside world, they look like one, but they're all IP addresses. And there's a special group of IP addresses called localhost. Localhost. There. They start with 127 dot something. Commonly 127.00.1, but 127.1.1.1 is also localhost. They're all the local system. The system knows that if that first number that, that means it's local machine. Okay, so that is localhost. Okay, and the expression that here's one of Francis's jokes: "There's no place like home," or in this case, localhost. Or want to be cool, this is also localhost. This is a v6 IP address because, as we all know, and it's a huge crisis in the world, maybe second only to global warming, is that the world is running out of these IP addresses. Back in the day, we thought that, having, 1, 2, 3, 6, 7, 8, 9, 7, 8, 9, and whoops, 1, 2, 3, 7, 8, 9, like that. We thought we can't possibly run out. There is no way we could ever. That's a huge amount of devices in the world. I mean, how many universities can there be that have a mainframe? I mean, that's like 5 numbers is enough. This is probably enough, honestly. Maybe that. There's only, what, 10,000 universities in the world would have a computer? So why do we even bother? So my goodness, that's unheard of. There's no way there'll ever be that many network devices in the known galaxy. Yes, we all know that didn't happen, did it? So now the world is in fact running out of IP addresses. They've gone from, this is called version 4, by the way. It's a v4 address. They've gone to a new one, which is a v6 address. v6 IP address. That's localhost. What does a real v6 IP address look like, you ask? I knew to ask that. Let's take a look. A v6 IP address. So v6 example there. There we go. Here are some v6 addresses. There. And these are, by the way, hexadecimal. So each one of these can have 16 values from 0 to F. Oh, actually 15 really. So I guess 16, 0. So that, as you can see, is an absolutely ginormous number of possibilities. And of course, there's no way that can ever run out, can it? Right? Yeah. Until we start assigning IP addresses to individual molecules in the new nano world, then we're going to go like, oh man, that was a dumb decision. But that's off in the future. So, okay. So IP addresses. So we're now in the network layer. IP addresses. This is now networking, actual computer networking, where we're doing actual communication between devices. These are just interesting to know, as it says. It's kind of nice to know they exist, that's fine. You should be aware of these ones now. These are where software starts to come in. This is now we're getting into software. Number 4 is the transport layer. This is just, once again, it's TCP. So we have IP, and now we have TCP, which is a actual transport protocol. There's really several. There's Tcp and Udp, and a couple others. As developers, we almost always will be using TCP or UDP. Those two are the big ones that we use. And you will know this. You will know that you're creating a TCP connection if you're doing network programming. By the way, we don't do a lot of actual network socket programming. It's like today and tomorrow, and that's it. Then we get into actually doing web programming, and all that stuff is abstracted away from us. But for the first 2 days, we'd like you to get familiar with really doing actual TCP programming, write some code. Today, it's fun. We're writing actually a client to a snake game, actually a multiplayer game, which is cool. It's no Slither.io, trust me. The graphics kind of suck, but hey, you write it yourself. And for that, we're using TCP. So TCP UDP. TCP is a fairly rigorous protocol, and UDP is less so. We'll talk about that in a second. Okay. Layer 5 is session. Don't deal with it a lot. This is more for communication between like devices. If you have more than one computer, you can do file sharing between the two. They can connect to each other. You can log into one. That's kind of session stuff where you have a concept of a session between two devices that are connected over TCP. And by the way, it's important to note these layers, they each take care of different things. So for instance, I'm up here on TCP. I'm doing some networking. I don't know what physical layer I'm using, and I don't care. This is one of those separation of concerns things in computers, that these layers, they don't care. Maybe we're talking about Wi-Fi right now. Maybe we're not. Maybe you're using an ARP, using a hardwire over Ethernet, or maybe you're talking to me over Wi-Fi that's connected via fiber optic. I don't know. I don't care, because that's not important. So these layers handle one thing. Okay. Is the transport layer and session layer the client server exercise? Yes, that's exactly what it is. We'll do an example here today as well. Yes, these are the, right there. These are, well, actually this and a bit of that. That's the exercise that we did with the client server stuff. And we'll do one today as well. So, okay. So these layers are independent. As long as this can plug into that, we don't care what's below it. So we have a TCP, and we're using, well, TCP over IP. We have TCP over IP. So TCP/IP. It's not TCP over ARP. It's not UDP over IP. It's TCP over IP. So when you hear the expression TCP/IP, that's what we refer to. The transport's TCP and the networking is IP. Things you didn't know. So when you hear the term TCP/IP, to your friends, you can go, hey, did you know that TCP/IP actually means layer 4 TCP over layer 3 IP? Wow. So you can wow your friends. Like, you'll be the life of the party. So use that as your opening line. It's you can open with that. It's great. Okay. So the session is, once again, computers talking to each other, more higher level. Then we get into the presentation layer. This is how the actual data is presented to the server. Handles things like compression, TLS. We can actually encrypt using TLS or compression using gzip. So we have TLS, SSL. These are the two main encryption methods for encrypting HTTP. So TLS is now the one we use. SSL is insecure, so we use that. gzip compresses stuff. Then we have, what we really care about is the application layer. As developers and web developers, this is what we talk to, the application layer. This is the big one. We talk to HTTP. And by the way, you notice we don't see HTTPS anywhere here, do we? Because if I go to my browser, chances are it's HTTP. It is HTTPS. It's everywhere. Well, it's still the HTTP protocol. This is HTTPS over SSL, or secure HTTP. But what I really refer to is HTTP over SSL. Of course, now it's TLS. So really it's HTTP over TLS. But HTTPT doesn't sound so cool. So it's still HTTPS because it was originally SSL. Okay. So that's what you're seeing. HTTP over SSL, which is probably over TCP over IP, probably using Wi-Fi over, eventually, or actually ARP over Ethernet, or Wi-Fi over that. So yeah, so HTTP over SSL, no session going on, so we don't care about that. Well, TCP again, really. So using TCP over IP, using ARP over Ethernet. Once again, the big takeaway is there is a thing called the layers of networking. And yeah, they're kind of cool. One of them has to do with cables. And like that was kind of it. So, okay. Take a really quick one on TCP, and we'll take a bit of a break here. So believe it or not, there's jokes on TCP. Computer guys are like the most interesting guys in the world. They make these really cool jokes because they can't make real life jokes. So let's take a short break, maybe a 10-minute break, and we'll come back in just a little while, and we'll carry on. So okay, and we're back. All right, let's carry on with our discussion of networking. So we talked a bit about these ISO layers, which we promptly forgot about, and it's just nice to know there is a thing called the ISO layers. That's all we need to get out of this. And kind of 1 is like the lowest level, and 7 is like where we hang out, and What's in between? I don't know. There's some stuff I just didn't remember from boot camp. So, all right. But eventually, really, you get to know kind of layer, 4 or 5, TCP. Okay, yeah, I kind of know TCP's in there somewhere. What layer is it? I don't know. I can't remember. It's 4 or 5 or 3. It doesn't matter. I know that 1 is cables and like 7 is like HTTP. That's all I know. Sorry. That's good enough. So let's talk a bit about TCP and UDP, because those are when we do deal with network development or actual like socket development, which isn't that common as web developers, but we do a little later on. What does UDP stand for? Cool. Great question. Awesome leading question. So when we do things like WebSockets, it's going to be kind of useful to have done this net programming, like with the Snakes application, the client server stuff. Oh, wow. I'm actually glad I did that with that silly Snakes game, because WebSockets kind of looks just the same. Isn't that cool? That's a lecture for a lot later in bootcamp. TCP and UDP. Let's take a look. What do they stand for? Okay, let's take a look. So what does TCP, RCP, stand for in Pokemon Go? That's interesting search result, isn't it? Okay. Transmission Control Protocol. Okay, that is really helpful. That explains it all. Don't need me. It's like everything there. And UDP, as one person has correctly pointed out, it's true. It is User Datagram Protocol. That says it all. I mean, how can I add to that? All right, so let's talk about what they actually are. This is not a long conversation because we want to get into some actual real stuff here. So we have TCP, UDP, the two most common things you're going to see. These two protocols, they're in the 4th layer, right? Although TCP is also sessions. They manage transmission of information. They manage what's called packets. So information or messages or data is broken down into packets. You may have heard the term packet size, and you can increase your packet size. These are technically what are called packet switched networks. My first job was at a telecommunications company. So we dealt with equipment that handled packet switch networks back when that was fairly new. They're all packet switched. They turn information into packets, and those little packets, little bundles of bytes or bits, go off down the wire as little bunch of zeros and ones down this wire. Packet switched. Do we need to know this? No, that's not important. Messages are broken down into packets. And these messages say where they came from and where they're going. So they have these like headers on them, right? Like there's a header on the packet. So I can take this packet and fire it down the wire there. And it gets sent along, different switch, it goes here, all around the internet, because it knows where it's going. So that packet of information goes through the network, even my house, up my street, into the main building, into the main ISP, but it's still got a little header on it. And it knows it's a little guy, come on, guy, you can make it. It's traveling all around the internet. And every stop along the way reads that header. Okay, who's this guy for? It's like mail. Oh, this is from this, IP address or something, and it's going to this IP address. Okay, I'm going to send it down here. So even though it could be 1,000 switches or routers in between you and where you're going, they all read those headers and route it the appropriate way, and it finally ends up on Doom or World of Warcraft or Google. And they send information back, and the same thing, a packet comes back to you all the way and ends up on your computer. So that's how information is transmitted on the internet or on the network in general, as packets of information. And they travel as an independent unit with a header. Who sent me? Which means where was I sent from and where am I going? That's the header on that little packet, and it gets tossed onto the wire, and you get a response packet back. Same thing. Okay. And packets are disassembled and reassembled when they reach the destination. They're reassembled back into the image or the music or the document or whatever it is they were originally before they were broken down into these packets. So, all right. So that's how they work. Now, TCP and UDP, they differ in how they handle these packets. If you send a packet over TCP, it's different from how it's handled if it was sent over UDP. So here's the two kind of general protocols. TCP, it's robust, lots of checks, okay, which means things are checked, they're verified. The packets absolutely, positively, without question, must arrive, and they must arrive in the correct order. So that's TCP. There's lots of acknowledgements. Did you get the packet? Yes, I got the packet. Are you sure you got it? Yes. What was the size of the packet? It was this big. Okay, you got it. Here's the next packet. A lot of work. You send a packet and you get an acknowledgement. Another packet. So that one packet's getting sent all the way down the internet. If perchance I sent a bunch of packets and one didn't make it, I got to stop and resend from the beginning again, or resend from where I left off, because they absolutely must arrive in the correct order. That's TCP. It's a very robust, has a lot of overhead. So it takes a bit of processing to use TCP, but it's robust. TCP is what we use on the internet. We use TCP. But we also use UDP as well. UDP, the only comment is meh, yeah, whatever. So basically not that, okay? So it means it's not that. It's not robust. There are no checks. You send a packet and forget about it. It's like tossing a rock. Okay, rock's been tossed. Let's toss another rock. Did they get it? I don't know. I don't know. Did it get received? I don't care. I don't know. Who cares? Just keep tossing rocks. Yeah, because I don't care if they receive it or even in the proper order. There's no guarantee of anything. As you can imagine, UDP is very fast. You can fire stuff off. UDP is used primarily for streaming. Right now, we're talking over UDP. So this communication, this video and audio is coming to you compliments of UDP. So brought to you by the good people of UDP. That's how we're talking. Because so what if one packet gets dropped in my music? It's like one out of maybe a 8,000 hertz thing. I'm not going to notice that at all. Who cares? So I am not going to use TCP as my protocol for sending music because it's extremely expensive and it's going to be laggy because it's never going to get it on time with all those checks. UDP, just stream. You just send it off. You don't care. There is no connection. You just say, here's the IP address. Just fire that stuff off that IP address. Don't even make a connection. TCP is what's called a connection-based protocol. You must make a connection first. So it's connection-based. You make a connection. UDP, there is connection-less. There is no connection. You just fire it off. Here's a packet, and here's what's going. Letter in a bottle in the ocean. There it goes. It might make it there, might make it there on time. So I'm going to send a bunch of bottles into the ocean, into the river, maybe, better analogy. And downriver, someone picks up those bottles and reads the messages. They might get there in order. There's a good chance they will because the river's flowing in one direction. But maybe one might hit a rock and get lost. One might sink. One might pass another one out of order. It doesn't matter. So when you don't care about things, use UDP. And that's almost all broadcast, networking, music, streaming, videos. That's all UDP. Okay, because it doesn't matter. Okay, this is compliments of France about it. Here's a joke about TCP. It's a really bad joke. Would you like to hear a TCP joke? Yes, I want to hear TCP joke. Okay, I'll tell you a TCP joke. Okay, I'll hear a TCP joke. Are you ready for my TCP joke? Yes, I'm ready to hear the joke. Okay, I'm about to send the joke. It's going to last 10 seconds and it has 2 characters. Has a setting, ends with a punchline. Okay, I'm ready to hear the joke. I'm sorry, connection timed out. Start again. It starts again because TCP restarts. If things didn't happen, timeout, it will restart and absolutely positively try to get you that packet no matter what. Okay. Not a great joke. Here's a better one. This is the UDP joke. I love this one. I'll tell you a joke about UDP, but you might not get it. Ha, that's awesome. I love that. Well, computer guys, that's funny. Come on. Isn't that funny? That's a great joke. Okay. Anyway, let's do a bit of recap of some TCP client server. Has everyone done the client server example yet? We have to write a little TCP client and server. Was that yesterday's work? I can't remember. Was it Tuesday or today? Maybe late. Mine didn't work. Okay, yeah. Mine didn't work first time either. So let's go ahead and do that. Let's actually make one of these. So I'm going to make, I think I have some empty files here. I do. Okay, client server. Let's write ourselves a client and server. So we'll start with the server. So knowing what we know that we're using TCP. It has a connection. So, and we're pretty much on layers, 4 and 5. We're doing TCP stuff, aren't we? So we're doing connections, TCP. There is no protocol yet. So we talked a bit about protocols. Let's look at our stack again. So right now, we're coming up with our own protocol. We're going to be writing our own stuff. Not dealing so much with presentation, but we're really going to be working with these two things. We won't do any of this, so we're kind of ignoring it. We're not compressing it. We're not encrypting it. We're not doing anything else. So we are programming a layer 7 application. It is going to make up its own protocol. So we are now programming for layer 7. It's an L7 application. That's not a thing. So we got our L7 application. We're going to make up our own protocol. So I'm going to make a server. Okay. So you probably know the first thing we have to do is we have to use the net module. So we're going to require that. And require net there. So now we have imported or required the net module. It's built in, so you don't have to install net, but you have to just say you're going to use it. I'm going to use net. Now I've got all these net dot things I can use. And servers are fairly simple. So make a new server. Const server equals, and it'll be net, which is this net here, this variable. This is now an object. I've imported this object. And who's going to know? Yeah, look at this. VS Code is smart enough to know I've got all these different methods on the net object. I'll create connection. Wow, create server. Cool. Is IP before 6? That's kind of cool. Wow. Okay, I'm going to use a create server. So create server. I want to create a server. No parameters needed. There. Now I have a server. Look at that. One line of code, and I have created a server with one line of code. Impress your friends. Okay. Tonight, do this. It's pretty cool. Okay. So now I have a server, but my server doesn't do anything. It needs to actually wait for stuff. So I'm going to have my server listen for stuff. So server dot, and there is a listen. Look at that. Listen, okay, for connections on a particular port. So we didn't talk a lot about TCP, but they're what are called ports in TCP and UDP. And a port is just a number. It's just a number between 1 and what's 16 bits with all 1, 65, 535. So between 1, 0, we can't really use, 2, 65, 535, which is 2 to the 16th power minus 1, right? Because it's odd number, okay? So pick a number. I'm going to use 3,000 or 4,000 or 3,001. Doesn't matter. Totally your choice. I would encourage you not to use the numbers below 1024, if possible, because they are reserved. They are reserved for other protocols. As we know, port 80 and port 443, those are HTTP. And while we certainly can use them, we have to understand that we are using ports that are used by other well-known protocols. Port 25 is used by email. Well, not anymore, 465 is, but it is used. So we steer clear of numbers below 1024 because they're commonly used. And if for those of you who are actually interested in this stuff, common TCP ports. Look at that. What are the common ports? And wow, overview, the 1,000 overview of common ports. Anyway, let's look at this. Let's take a look. What are the common ports? Okay, not that many. There's a lot more than this. Like there's that. So how about this? Is there more of a list? A list of. This promises to be fun. List of port numbers. What is this? Here we go. There we go. Wow. Lots of them. What is this? Amiga Envoy Net. What is that? Amiga Envoy Network. Who knows what that is? But apparently someone has it reserved as a common port. No freaking idea what that is. Oh, Amiga, hold on. Let's show a picture of Amiga. Where'd it go? Oh yeah, look at that. The Commodore Amiga. Actually a really good machine apparently. I never used one, but I heard they're a really cool machine. That kind of predates me. Wow. With 256K or more of RAM. Wow. That was actually ahead of its time. It's 32-bit processor back then. That's like freaking awesome. So, okay. So lots and lots. Look at this. Tons of them. Wow. Here we go. Okay. So 1023. There we go. The ZFS. After that, you're pretty okay to use some of these ports. Some are commonly used, but you're okay. Like 5432 is Postgres. We'll use that later, but you're not so bad using it after this. So kind of use what you want. There we go. They're still used. I mean, apparently, look at this. Port 3000 is in fact used by somebody, but it's not one of the real official reserved ports. These are the kind of the real, well-known ports assigned to protocol. Can we use anything we want? We can use anything. It doesn't matter. We could use 25 because I have no email server on this machine. Who cares? I'll use 3001 just because I'm going to use one over 1024. It doesn't matter. Just bear in mind that some of these numbers are reserved and they might have conflicts with something else should you use them over the internet. Okay. In my case, my server is going to listen on port 3001 because I like that number. Okay. I have a server. Let's see if I can run my server. Let's take a look. Terminal, because we need 2 terminals there. I'm going to run my server. Node server.js. Well, it didn't crash. That's a plus. It's not doing anything, but it actually is listening. This server is in fact listening on port 3001. It is not saying anything at all because, well, I didn't say anything or print anything on my program. So it's outputting nothing. So I can control see that. So far, that's a win, no crash. Okay. So now I, of course, need to have my server do something. It's listening, but now I need to have it do something when somebody connects to it. This is connect, by the way. It's a listen. I say it defaults to TCP as a listen. Okay. So I want it to listen for connections, and this is an event handler or a listener. This is a common concept in software development. You will see this quite often. We'll be doing a lot of this in 2 weeks when we get into jQuery, which, by the way, is really fun. We have listeners listen for certain things to happen. And so I have my server, and I want to listen on a certain event. And there's an on function. It's called the on function. So listen for the following thing, or when this happens, do this. We call it on this, or so on connection, or on disconnect, or on data. So it usually has the word on. So that's why I use the function on. It's called on. In this case, it is on connection. When a connection happens, connection. This is a string, but it will see an event with the string connection in it. It'll hand that. So server on connection. This function takes 2 parameters, the on function, the thing to listen for, and what to do when it happens. Remember our async stuff? Well, it's going to be a function, isn't it? This is going to be a function. Now, I could write a function that handles connections. I certainly could. Or I can put it inline. You'll see it both ways. Let's take a vote. Inline or make a function, make a callback named function. I can make a function here. No. Connection callback. Oops. Connect. There. Connect callback. Or inline. I have 1 vote for inline. Anybody else? Come on. So far, the inlines are winning. It's one vote. It's like an election. If you don't vote, you can't complain. Inline either, okay? So we can use just a function name like this, like that. There. So there's the function, okay? It could also be an arrow function. Could be this as well. That works too. Anybody comfortable with arrow functions, functions? I'm okay either way. Let's take a vote for that at least. Who votes for the cool arrow function inline thing? And who votes for the also very cool function? It looks like arrows win the day. And wow, look at that voting. I guess this is one of those issues that the voters do care about. That's every politician's dream. Find out what they actually care about. Apparently, they really care about what kind of function. Okay, so here's a fun fact. Arrow functions are great for inline functions. They are great. And best practice is to use them for inline. For named functions, while we will see a lot of junior developers giving functions names with an arrow, it's not as commonly done among senior developers. So it is perfectly valid, but and some companies even have it as a policy, but generally what's generally accepted is if it's inline or as an anonymous function, make it narrow for sure. But if it's a named function or certainly part of an object, use the function keyword. Which did you choose? It doesn't matter. It doesn't matter. Maybe your company will have some policy and they'll say, no, named functions have to have the function keyword and that's it. So it doesn't matter. Nobody cares. I'll use an arrow function because that really should be your go-to for inline functions. Okay, now this is a callback inline, but I'm going to get back what's called a socket. I can call it anything. I'm going to call it socket because that's kind of a technical term. You get back a socket. When this callback is called, remember when this is ready, I'm going to get this function executing. I'm going to get a socket back from my server, okay? Which means somebody connected. I'm going to console log. So I can log connected. Someone connected. Connected. Yay, and string, of course. There. Someone connected to me. Great. Okay. So now I can run my server, and let's actually make a little note here. Let's say server listening on port 3001. You'll commonly see this in your applications. So I'm listening. Let's run my server. Hey, it said something and it's listening. That's great feedback. Let's go ahead and use another terminal. You notice, by the way, that I am not using this, am I? I need two windows. Later on in the bootcamp, you're going to probably have 4 or 5 of these open. Use a real window if you can. These windows, although they're great for doing demonstrations online on YouTube, this is not so useful for like showing people your code, is it? Like, yeah, where's my code? So yeah, I don't normally use these terminals. Okay. Okay, let's connect. Now I'm going to connect using a built-in TCP client that's built into Unix or Linux. It's called Telnet. So I'll use Telnet to install or to connect to my server. Let's try it. Telnet to a local host on port 3001. Oh, someone connected. Wow, look at that. Nothing else. Of course, nothing's happening. My server doesn't do anything, but someone did in fact connect, which is great. Someone connected. Let's try it again. Someone connected again. Wow. And quit to quit. Okay. Okay, so my server's working. I'm getting connections. This is cool. Let's do something else. Let's create another listener. And this time we'll handle the event where somebody hangs up on us or someone disconnects. So it's very similar, but all subsequent operations for this particular client session take place on the socket because this is the client. So everything else that we do takes place inside here. So if the socket hangs up on us or disconnects or someone leaves, I'm going to use the socket.on function, and I'm going to listen for things that happen on the socket. In this case, I want to listen for end. If the socket ends, I'm going to handle that with a function or arrow function. And I'll just console log that the client left. Okay, so now I'm handling the case where the connection has been disconnected, and let's give that a try. Okay, so we'll restart our server. Okay, and let's run our connection again. So someone connected. So now I'm going to disconnect. Quit. Client left. Great. So far this is working fantastic. Okay, let's add something else. Let's maybe send the client some data when they connect. So when they connect, we're going to send them something. So why don't we, at the very end here, we'll just socket.write, and we'll send them something. We'll say hello. We'll say, hello, you are connected. Right. Okay, so now I'm sending information. Once again, it all takes place inside the connection listener. And I will send the user, hello, you're connected. And I'm still listening for the end event. Let's try it again. Restart this. Okay, and let's run it again. Actually clear so it doesn't take up screen space. Okay. And look, I got hello, you are connected back from my server. It's exactly what I expected. Okay. And when I disconnect, connection closed, client left. So great. So now we're on our way to having a fully functional server. Let's do one more thing. Let's respond to some data that we might get back from the client. So that looks like it might need another listener. So as you can probably guess, that's another socket.on there. And this time I'm going to listen for data. I'm going to listen for some data. And this time I'm going to get a parameter in my callback. There. And I'll log the data. See what I get. Okay. So now we're listening for our data. Let's restart our server and connect again. Okay. Now if we type something, hello. Well, that's interesting. We did get some data, but it's actually as a JavaScript buffer. So let's just set our socket set encoding. We'll socket.set encoding to UTF-8. Okay, we'll stop our server, start it again, and we'll run this. And we'll say hello, and we get the word hello. The reason we got hello was because we had encoded it as UTF-8. We told the server, oh, anything you get is going to be text UTF-8. If we had removed that, what we would get, we'd get back a JavaScript buffer, which could contain binary information. But we're saying, no, don't worry. Everything that the client sends to you is going to be UTF-8, which means you can interpret it as actual strings and text. How we do. So hello again. Again. Hi there. So it's all working. Let's do one more thing with our server. Let's now send the same data back to the client. So socket.write. Now we're at the same data there. So now we are essentially what's called an echo server. We're an echo server. Anything that the client sends to us, we send right back. These are very useful sometimes when you're testing clients or servers. You can say, well, did something get sent back? Well, let's try the echo server. Let's run Telnet. Connected. Now it's going to be hello there. And we got back hello there. Hello. Hello. Ah, it's an echo. It really works. Okay. So this is working great. So I now have an echo server. Okay, so quit, client left. Great. So we have, it looks like we have a really great working server here. So now we're going to create a client. Now a client starts off the same way. We'll const net equals require. So we're going to require our same library, our same net library. And make a connection. Const connection equals, but this time we're going to use net.createConnection. The create connection function allows us to connect to a server. So create connection takes as a parameter, it takes an object. And in that object, you can have two things, host and port. The host is going to be localhost, which as we know is 127.0.0. something. And the port can be really any port we want, but we know that this server is listening on port 3001, so it needs to match what the server is listening for. So there's our create connection. And we're going to add an event handler or a listener to see when we connect. So connection dot on. And we want to know when we connect. So connect. And when we connect, we're going to run our function, the callback. How is console log connected? Why not? Console log connected. Let's try our server. Let's restart our server. And now we don't need our telnet anymore. And now instead, we're going to run node client.js. Okay. Looks like it's working. We got a connection. Okay. So we can stop our client. We can leave our server running now because we're not really going to do anything with our server. It's kind of running fine. We know it's a really well-working echo server. Let's add some things to our client. Let's also listen for data. Do the same thing. Connection dot on, and we'll listen for, just like on the server, data. And that callback is going to take the data incoming and our function. And well, we can just console log our data, can't we? So log our data. That's all we care about. Okay. So now we're going to console log what the server sent to us. Let's try it. Run our client again. And we got a buffer. Because we didn't specify the encoding. So with no encoding specified, you will get back a buffer object, which can contain binary information. So what we need to do is to set our encoding. And we can take that from our server because we did the same thing right here. Okay, and we'll do the same thing with our connection right there. So this is going to be connection dot set encoding UTF-8. So let's try our client again. And now we get hello, you are connected, because now both sides agree that they're speaking UTF-8. Okay. One more thing. Let's send some data to our server once it connects. So this is going to be here. We're going to connection dot, much like before, it'll be connection dot write there. And we're going to write the string hello there. We're going to write hello. Let's try it. Hello. And I got hello back because that was the hello I sent there. And that was the hello I got back in my data listener. So great. So this is the fundamentals of client server. On a server, you create your server and then you have a on connect, and everything that you do or handle for that client takes place in here. And you can listen to different things on that socket you get back. In the client, it's a bit simpler. You simply create a connection, and that's all you have to worry about. And then you can simply listen for things happening on that connection. And you can write. Okay. So that's really the quick overview of client server. So now let's carry on and we'll talk about TCP protocols. Protocols are a language that are used right at the layer 7. So right now we had our protocol was like hello server. We made it up. But there are official ones. HTTP is an official protocol. SMTP is an official protocol for sending emails. There's a lot of official protocols of ways that applications talk to each other. If you have an HTTP application, it needs to talk to an HTTP server in a specific way. That way you know that your HTTP client will always be able to talk to an HTTP server because you're talking the same language. So we've agreed on a language or a protocol to talk to each other. And the protocol for HTTP servers is, of course, HTTP, which is fairly quite complex. It stands for Hypertext Transfer Protocol. And that's what we used for talking to web servers. It is request-based. Now, this you should remember. That OSI layer stuff, you can like back of your mind. But request-based, that is something that's important to remember. It is request-based. The client always makes a request of the server, not the other way around. So the server responds to requests. You request something, you get something. You want something else, you request that, and you get something back. You want to change something, you send a request to change something, and that gets changed, you get a response back. It's always requests. And of course, it's a request and a response. So it's always request response. You will hear this, and this is something you need to know. Request response. It's a very common concept in web development. What was the request? What was the response in the client server? Clients make a request, servers send the response. The initial step of an HTTP exchange is the request. So your application or a browser makes a request. It sends a request packet, if you will, to the server, and it gets a response packet back, or multiple packets, depending if it's larger than your packet size. Okay. Why don't we do an example of a request? Here's are the different types of requests. HTTP has several different methods. It has a GET and a POST. These are by far the most common. Has a put and a delete as well, and patch is not commonly used. So those four, GET, POST, PUT, and DELETE, those are the ones that we use, and these two are very, very common. And when you browse the web, the majority is using a GET. Get me that page. You send a GET request to an HTTP server, and it sends you back the page for that they've asked for that URI. We have these URIs, URL, and they are used almost interchangeably. Technically, they are different things, but you will find people use these two terms interchangeably. URL, we've all heard that. What's the URL? we're going to do an example of a GET using our good old friend Telnet again. Telnet, there we go. But now let's Telnet somebody else. Telnet www.google.com. Google.com. Let's Telnet on port 80, although we know we should use 443, but it'll still respond on port 80. Look at that. I'm connected to Google. Like I'm literally connected now to Google on my Telnet. Isn't that awesome? I have an actual connection established. It's TCP. So their server has responded with it's on connect. I can now send HTTP requests, and we can send a GET. They look something like this. I can send a GET. Let's send a GET. I'll send GET space /. And you have to tell it how you want it. And I use a protocol. We'd say, I want HTTP 1.1. So sure. HTTP P1 /1.1. So I'm actually talking directly to the Google server. I'm sending a request. Okay. Here the Telnet is connected to Google. Yes. Well, I'm making the requests. So the client or the Telnet client here, I'm still using that as a client, as really a raw terminal into Google's web server. I am on the Google's HTTP server making requests. When I hit enter, look at that. I got a web page back. It looks like HTML, right? Anyway, so there's my request. There, start here. So there's my GET. Okay. I got back some header information. So this is a response. That was my request. GET space / space HTTP 1.1 and then an empty line. Okay. I was talking to the Google server directly. I hit enter, then a blank line. Google server says, oh, great. There's a request. It's a valid request. It sends me back a response, an HTTP response. This is a valid HTTP request. I got back an HTTP response. I got back the initial header, okay. Then I got back some header information. The response contains the header and the body. So I got a header there, and I got a body. There's my header. So the header, let's take a look. So the header contains some useful information. It says, well, there's the time of this request that you sent me. It doesn't expire. You can cache it if you want. That's what I'm sending you this content. Oh, you're getting back text /HTML. So just so you know, this is what you're getting. So when you render this, you can know this is text HTML. So my browser knows, oh, I'm going to show this as HTML, not as something else. Maybe it was text /plain. Maybe it was an image. Maybe it was JSON. Maybe it was something else, like a movie. It would render it differently. So this is a very important header. What was the content type? Some cookie stuff. We'll talk about cookies next week as well. So this is me talking directly to Google server. I have a terminal session into Google right there. Oops, it's long. If I give it garbage, I'm going to get garbage. That's an error, right? So it didn't like that. Whatever I typed, it did not like a bad request. I got a 400. So interesting. I got a 400 status on this one, but I got at the very top, where to go, a 200 request here, there, 200 okay. This is called the response status. There are quite a few response statuses you can get from a server. Let's take a look. HTTP status codes. There's families of them, 100, 200, 300. The 200, these are the good ones. This means, yes, things worked okay. 300 means, well, mostly redirect, sent someplace else. 400, 500, something messed up. Either you did or the server did. You got a 400 back, means you screwed up. And on my request, where is it here? I got a 400 status right there, which means I screwed up. I done something wrong. So if the server had an error, which is a bad thing, it would say a 500 error, which means, hey, we have an error on our end. It's not your problem, it's our problem. So let's look at our status codes. These are really cool. There's a whole bunch of status codes. Take a look. Go to the Mozilla site. This is a great one. Okay. There's lots of these. Hold on. So here's all there. So 200. Okay. The request has succeeded, which means you're great. All is good. 201 means we've succeeded and we created something for you. A 204 means there was no content, but it was still good. So a bunch of 200s. These are all good responses. Cool. You don't see a lot of 100s either, really. So, okay, this is the HTTP status code. Let's go to some of the other ones. 300. That URL has moved. You should go someplace else instead. And it will send you, it'll tell you where to go. 302, you'll see a lot too, which means this has moved. You should go here instead. We use this a lot next week on your first web app. We will respond to redirects or we'll send redirects a lot. Okay, there, lots of 300. Look at this. Wow. Okay, client response errors. So this is, you have a problem. Bad request, 400. Your request is just generally bad. I can't say anything else. It's just generally a bad request. And that's what Google did. 400. It was just in general a bad request. It couldn't even tell me if it was like something else. It's just bad. Maybe it's not authorized. Maybe it saves a password. Maybe it's forbidden. You can't access. Not found. Anybody see 404 not found on the browser? Come on. Everyone has seen 404 not found. Of course we have. That's a status. 404. Not acceptable. That is not an acceptable request. I'm sorry. That is unacceptable. Conflict. Look at this. Gone. Some of these are kind of obscure. Gone. Hey, I'm sorry. This is just gone. We don't have it. Right. Too long. Look at this. Wow. I'm a teapot. That is an official HTTP status code. I'm a teapot. I love that one. Isn't it awesome? That means that the server will not brew coffee with a teapot. That's obvious. No explanation required of that one. So yes. So what it means is you're asking me to do something that like totally doesn't make sense. Like you've given me a teapot and you said to brew coffee with it. Like what the heck? So it returns a status 14. I'm a teapot. Love that one. Okay. So lots of status codes in HTTP. So as you can see, you can make requests of HTTP servers. If I go into anyone, google.ca, which is a different one. Same thing. Get / and use HTTP 1.1 again, and give it a blank line. I got a response, and slightly different response, but I got a web page back. So, I mean, this is all lots of fun, but I mean, we wouldn't normally be doing this. We wouldn't be normally talking directly to a server over Telnet, other than to see if it works. So this is what browsers do. Now, we talked about this thing called the browser. Let's go to one of these. There's a browser. I'm using Firefox. Chrome is the same. So popular browsers, Edge, Chrome, Firefox, they are browsers. And that is what they do. They make HTTP requests. That is their job. So when I type in this www.google.ca and I hit enter, what my browser is actually doing is this thing. It's sending that. So I hit that, I hit enter, it sends that, and it gets this HTML, this just stream of bytes back, and the browser renders it with an image in it as a web page. That's what's happening behind the scenes. So let's take a look at what really happened. You can do this using our dev tools. You can either go view dev tools, or F12 works too, by the way, on many machines. Just F12 pops up and you can go network and refresh the page, and there's a request. Now there's a lot of it happening here, but where's my original get? Let's just clear the page with the original get. And I believe we can filter stuff out. We just want to see HTML only. There. Okay, we'll hit enter. There. There is our original get. Get /. There's my request. Oh, look at that. See, there's the get. that was sent, and HTTP/3 it asked for. Oh, that's kind of cool. What was the request? Sorry, there's a request. I said get that, and I said use HTTP/3. I got back a status of 3. So there's my response headers. Look at my raw header. There. Doesn't that look familiar? There's the header I got back from Google in my browser. Looks a lot like the stuff we got back in Telnet. Okay. Date expires -1. Look at that. Useful stuff. And of course, there's also what's called request headers. In my Telnet, I didn't send any request headers. You can also put headers in the request. Extra stuff. Like it's okay to compress stuff you send back to me. Little things like that. So there's headers on both sides. As you can see, we can query or show the results of our requests in our browser. And that's what browsers do. Anyway, so that's our brief introduction to networking HTTP. It's a pretty big field. I mean, it's all kinds of stuff, all the layers, which you don't need to remember, really. Just there are layers. TCP, yeah, you should kind of know what TCP is and TCP IP. You should know something what a protocol is, that there's this thing called protocols, and one of them is HTTP. Good one to remember. Probably know that HTTP has a request and a response, and there's these header things and a body that you get. You get the header first, and you get a status. So status, header, and body. And it has response and request. That can both have headers and a body. A GET has no body. And we did a little bit about talking about how browsers operate. And you can actually look at the stuff in the browser and inspect the request and the response that you're getting back from the browser. This is cool stuff. You can actually really inspect this stuff and see what on earth is going on in this request. All right, everyone. So we'll